let's start it. Z transform. Z transforms. In case of continuous time signal, we do Laplace transform and Fourier transforms. And in case of discrete time systems, we will do Z transform and discrete time Fourier transforms. Like analogy, Laplace transform is similar like Z transform in discrete time systems. Fourier transforms is same like discrete time Fourier transform. In case of Laplace transforms, let's review the Laplace transform things. In case of Laplace transform, the variable was s equal to sigma plus j omega. S is a complex variable where sigma is the real part and omega is the imaginary part. This is the S plane, here complex plane. Here the x-axis is the sigma real axis and it is the imaginary axis. So S covers the entire the complex plane. So the definition of the Laplace transform like s of x of s. Suppose x of t is the continuous time signal and we want to take the Laplace transform of this x of t. The Laplace transform of the x of t, which is x of s, equal to from minus infinity to infinity, integration from minus infinity to infinity, x of 2 x e raised to the power minus st dt, where s equal to sigma plus j omega. By putting s equal to sigma plus j omega, we get integration from minus infinity to infinity, x of t e raised to the power minus sigma t e raised to the power minus j omega t dt. This is the Laplace transforms. The Laplace transform is the generalized transform and the Fourier transform is the special case transforms. Meaning, this is the Laplace transform where s is replaced by sigma plus j omega. But in case of in case of Fourier transform, we put sigma equal to 0. Means this real axis equal to 0. So by putting sigma equal to 0, we get integration from minus infinity to infinity, x of 2 e raised to the power j omega t dt. This is the Fourier transforms. In case of Laplace transform, our ROC or region of convergence was the complete real axis and complete imaginary axis. At a real axis, we can go from minus infinity to positive infinity. Also, at imaginary axis, we can also go from minus infinity to plus infinity. Means we can complete the entire S plane in case of Laplace transform. But in case of Fourier transform, we put sigma equal to 0. When we put sigma equal to 0, means this real axis is 0 and we take only this imaginary axis and we take the Fourier transform at only this imaginary axis of the S plane. Region of convergence. This is the region of convergence. Region of convergence means in case of Laplace transform, suppose sigma is defined by the region of convergence. If sigma is greater than sigma naught, here is the sigma, the real part is sigma. Suppose at any point, this is the sigma naught point. Sigma is greater than sigma naught. This is the sigma naught point. Sigma is greater than sigma naught means this right hand sided entire S plane is a region of convergence. In any case, suppose there will be sigma is less than sigma 1, means this left hand side is sigma is less than sigma 1. This region will be the region of convergence. If in any case where we take sigma is greater than sigma naught, suppose this sigma naught is in negative real axis point, this sigma naught point is located at negative real axis, then this entire ROC region takes the imaginary axis. And this is the most important point to note, that if this imaginary axis, if this j omega imaginary axis comes under this region of convergence, then we can say this this Laplace this function x of t have Fourier transform. Fourier transform of x of t will exist if this sigma naught includes this j omega axis. If this j omega axis is included inside this ROC, then we can say this Fourier transform will exist. Because to get Fourier transforms, just we have to take this imaginary axis, j omega axis. When this region of convergence takes this j omega axis, then we can say Fourier transform will exist. If in any case sigma naught is here and sigma is greater than sigma naught, means our region of convergence is this area, then it does not take this j omega axis, means we can say their Fourier transform does not exist. Okay, Now the Z transforms. Z transform is generalization of discrete time Fourier transform. Like Laplace transform, from Laplace transform we get, means we are saying Fourier transform is a subset of Laplace transform. In similar case, discrete time Fourier transform is a subset of the Z transforms. Like in case of discrete time Fourier transforms, x of e raised to the j omega is summation n from minus infinity to infinity x of n, our signal, input signal x of n e raised to the power j omega n. This is the discrete time Fourier transform. And the Z transform is x of z summation n equal to from minus infinity to infinity x of n z raised to the power minus n. This is our the x of n signal. This is our the x of n signal is similar. Here e raised to the power zn. Here z raised to the power minus n. Where z is r e raised to the power j omega. Means z raised to the power minus n means r raised to the power minus n e raised to the power j omega n. In case of discrete time Fourier transform, we take the r equal to 1. We take the r equal to 1 and the omega is from 0 to 2 pi or minus pi to plus pi. 0 to 2 pi is omega and r is the radius is 1. But in case of Z transform, our r is from 0 to 0 up to infinite. Means this in case of discrete time system is bounded across this unit circle, but our Z transforms is Z transform takes the entire complex plane. In similar case, our discrete Fourier transform in similarly Fourier transform is only at j omega axis, but Laplace transform covers entire the S plane. Discrete time Fourier transforms takes only a unit circle, and Z transforms complete the entire S plane. Here S variable is in terms of sigma plus j omega, but here Z variable is in terms of radius and radius means distance, and theta is the omega here is the omega is the angular frequency and r is the radius. Means here in case of continuous times Laplace transform of Z or Fourier transforms, here sigma and j omega is a variable, but here the variable is the radius and angular frequency, which is angle theta. Next, Z transform is the discrete time counterpart of the Laplace transforms. Similarly, Z transform is the discrete time counterpart of the Laplace transforms. Means in continuous time systems we take Laplace transform, but in case of discrete time system we take the Z transforms. Discrete time Fourier transform. In case of discrete time Fourier transform, Z equal to e raised to the power j omega, where the magnitude of the Z is e or r equal to 1. But in the general form, Z equal to r e raised to the power j omega. In Z transform, we take Z equal to r e raised to the power j omega. In discrete time Fourier systems, Fourier transform, we take Z equal to e raised to the power e raised to the power j omega. Here radius is 1, but in case of Z transform, here radius is from 0 to infinite. Means Z transform takes the entire S plane, but the discrete time Fourier transform takes the only a unit circle. Definition of the Z transform is like x of z, the Z transform is summation n equal to minus infinity to infinity x of n signal x of n z raised to the power minus n, where the z is r e raised to the power z omega. Z raised to the power minus n means r raised to the power minus n e raised to the power minus z omega n, means summation n equal to minus infinity to infinity x of n r raised to the power minus n e raised to the power minus j omega n. Next, summation n equal to minus infinity to infinity x of n r raised to the power minus n e raised to the power z omega n. If suppose this is the Z transform, this is the n is the my time domain signals, and x of z we will get at the frequency domain signals. In case of discrete time Fourier transform, we take x of n input, time domain input, and multiply with e raised to the power z omega n. But if we take time domain input as x of n r raised to the power minus n. X of n is scaled with r raised to the power minus n. Let's suppose this is our time domain input and x of n r raised to the power minus n. This is our time domain input and we want to get the frequency domain output. Then in a similar case, the discrete time Fourier transform of x of n r raised to the minus n, where r is belongs to real number and r is greater than or equal to 0. Okay, x means discrete time Fourier transform and the z transform is similar. In case of discrete time Fourier transform, our time domain signal is just only x of n signal. But in case of z transform, our time domain signal is x of n scaled with r raised to the power minus n. X of n r raised to the power minus n is our time domain signal in case of z transform, but in case of discrete time Fourier transform, our x of n only the signal at the time domain. This is the basic understand between the z transform and the discrete time Fourier transform. So we represent x of n and take z to get x of z transform, and we also take inverse z transform. The next is z transform of x of n is similar like discrete time Fourier transform of x of n r raised to the minus n. That is I am saying z transform of x of n is similar as discrete time Fourier transform of x of n r raised to the minus n. Condition for existence like discrete time Fourier transform existence uniform convergence. This is the condition for the existence that this x of n r raised to the minus n, this is the time domain signal that must be absolutely summable. Absolutely summable means the summation of modulus of this input of this time domain signal from minus infinity to infinity must be less than infinite. This is the absolutely summable condition. This is the ROC, region of invergence. Region of convergence means the range of value of r for which x of n r raised to the minus n is absolutely summable. This x of n r raised to the minus n must be absolutely summable at that a particular range. This range will be the ROC or region of convergence. Region of the convergence depends on the value of the r. Region of convergence, it is the region of the complex plane that depends only with the value of r, means the radius distance. It does not depend any angular value. If the z transform exists for one value of r, that is z equal to r e raised to the power j omega naught, then z transform exists for all points on a circle with radius. Means I am saying this is the suppose a z transform exists in between this r region, then at any angle, this is the angle of omega, this is the angle of suppose omega 1 omega 2, at any angle z transform also exists, but the boundary is defined by this radius r. Suppose a ROC, this is the circle R1. Here the ROC can be z modulus of z greater than R1. Modulus of z greater than R1 means this entire S plane except this inside the circle. Modulus of z less than R1 means inside this circle. Similarly, in case of another circle, this green circle, the modulus of z is greater than R2 means this entire regions except this big circle is will be region of convergence. Or modulus of z will be less than R1 means inside this small circle. These are possibilities. Or modulus of z can be greater than R1 or less than R2 means inside in between these two circles can be the region of convergence. The region of convergence cannot include any pole. Pole means suppose a transfer function h of x equal to p of x by q of x. The p of x, the 0 of p of x, the p of x is equation, polynomial equation. The 0 of the p of x is the 0 of the h of x, and the 0 of the q of x is the pole of the h of x. The ROC never include any pole. This the boundary will be the pole. The ROC never included this boundary. Okay.